Hello! In this video, we're going to look at some example problems where we practice writing proofs. So these example problems come from Daniel Velleman's book. So it's pretty much going to be some basic set theory problems and some basic facts we're proving about the real numbers. So let's start with this example problem. Suppose A set minus B is a subset of the intersection of C and D, and X is an element of A. Prove if X is not an element of D, then X is an element of B. So we're trying to prove a conditional statement. And to do that, well, one way we could try is by proving it directly. Can we show, under the assumption that X is not an element of D, that X is an element of B? So for our scratch work, let's try a direct proof first. Can we show, under the assumption X is not an element of D, that X must then be an element of B? So let's make the assumption X is not an element of D, and we'll try to logically deduce that X is an element of B. Let's see, what are we working with here? Let's write down the other things that were given. So we know that A set minus B is a subset of the intersection of C and D, and we have X is an element of A. So X is not an element of D. Well, at first, you might not see exactly what to do. So if you can't see exactly what to do at first, maybe we can try a different technique. Another technique we could try is by proving the contrapositive of the statement. And what that means is, if we can prove if this is false, then this is false, that will prove this implication. So the contrapositive of this statement is, if this is false, then this is false. So I'm going to write that out. So contrapositive, it tells us if this is false, then this is false. So if X is not an element of B, then X is an element of D. These two statements are logically equivalent. So if we can prove this statement, that proves this statement. This is what we call proof by contrapositive. So let's try to prove this statement. So let's make the assumption X is not an element of B and try to logically deduce that X is an element of D. So making the assumption here that X is not an element of B. From here, let's try to logically deduce that X is an element of D. So let's see, X is an element of A and X is not an element of B. That's precisely what it means by definition for X to be an element of A set minus B. Right, to be an element of this set means you're an element of A, but not an element of B. So X is an element of A set minus B. But we also know that A set minus B is a subset of the intersection of C and D. What that means is that every element of A set minus B is also an element of the intersection of C and D. So in particular, since X is an element of A set minus B, X must also be an element of the intersection of C and D. That's what we get there, but for X to be an element of the intersection of C and D means that X is an element of both C and D. So in particular, X is an element of D. And that's it. We have logically deduced X is an element of D. So under the assumption that X is not an element of B, we can logically deduce X is an element of D. So we can prove the contrapositive. But because these statements are logically equivalent, that tells us that the original statement we're trying to prove is true. Right? That's proof by contrapositive. So we're ready to write the proof. Because we're doing a proof by contrapositive, to start the proof, let's first state that we're going to prove the contrapositive of this statement. Right? I'm just going to write, we're proving the contrapositive. So that means we're going to prove this statement. So we'll make the assumption X is not an element of B. From here, we will logically deduce that X is an element of D, following what we did in our scratch work. So the observation was, since X is an element of A and X is not an element of B, that means X is an element of A set minus B. But then, using the fact that A set minus B is a subset of the intersection of C and D, well, that means every element of this set is also an element of this set. So since X is an element of this set, that tells us X is an element of this set as well. So X is an element of the intersection of C and D. So since X is an element of the intersection of C and D, by definition, that means X is an element of both C and D. But in particular, the thing we care about is that X is an element of D, so I'm going to say, so in particular, X is an element of D. So we've arrived at exactly what we wanted to arrive at. All right, we've shown under the assumption X is not an element of B, it follows that X is an element of D. So we have proven this implication. I'm going to write that down. But this is equivalent to the statement we were trying to prove. So we have proven if X is not an element of D, then X is an element of B. And that's it. That was exactly what we're trying to prove. So this completes the proof. So now, let's look at another example. Suppose the intersection of A and B is a subset of C set minus D. Prove if X is an element of A, then if X is an element of D, then X is not an element of B. So it seems like we have two conditional statements together at once, but really overall it's just one conditional statement as a whole, right? The overall conditional statement is if this is true, then this is true. So to prove the entire conditional statement, we're going to try to prove it directly. So under the assumption that X is an element of A, can we logically deduce that this statement is true? So let's go to scratch work. So let's make the assumption X is an element of A. And we're going to try to logically deduce that this implication is true. So you know what? I'm going to write goal. So our goal is to show if X is an element of D, then X is not an element of B. To prove our goal, we're trying to prove a conditional statement. So one option we have available is we could try to prove it directly. To prove it directly, we would make the assumption X is an element of D and try to logically deduce X is not an element of B. So let's see, what if we make the assumption X is an element of D? Can we logically deduce X is not an element of B? Well, if we can't think of anything right away, maybe instead of trying to prove this directly, maybe we could prove the contrapositive, right? So the contrapositive of this statement says if this is false, then this is false. Or in other words, the contrapositive, it tells us if X is an element of B, then X is not an element of D. So let's see if we could prove the contrapositive. Again, if we can prove the contrapositive, well, we know that this statement is logically equivalent to our goal. So if we prove this statement, that means we have proven our goal, which is what we want. So we'll make the assumption X is an element of B, and let's see if we can logically deduce that X is not an element of D. Well, let's see what we have here. We have X is an element of A and X is an element of B. So that tells us X must be an element of the intersection of A and B. But we know that the intersection of A and B is a subset of C set minus D. Everything in the intersection of A and B is also an element of C set minus D. So in particular, X must be an element of C set minus D. So we'll just write that down. But what does it mean for X to be an element of C set minus D? That means X is an element of C and X is not an element of D. So in particular, we have X is not an element of D, which is exactly what we wanted. So we're done. We see if X is an element of B, we can logically deduce X is not an element of D. So that proves this statement. And, well, we know that this statement is logically equivalent to our goal, so that means we've proven that our goal is true. But remember, we have proven our goal under the assumption that x is an element of A. So that means we have given a direct proof if x is an element of A, then this statement is true, which is overall what we wanted to prove. So we're ready to write up our proof. So, start of our proof. Overall, we're trying to prove this statement, and we're proving it directly. So we make the assumption x is an element of A. From here, we are going to logically deduce that this statement is true. And to do so, we proved the contrapositive. So I'm going to note in our proof, we're proving the contrapositive of this statement. Which means we're proving this statement, right? We're proving it directly, so we assume x is an element of B. And from here, in our scratch work, we're able to logically deduce x is not an element of D. To do that, our first observation was, since x is an element of A and x is an element of B, that tells us x is an element of the intersection of A and B. But then the thing we noticed was, since the intersection of A and B is a subset of C set minus D, that tells us everything in this set is also in this set. So in particular, x is an element of this set. So x is an element of C set minus D. What does it mean for x to be an element of C set minus D? That means x is an element of C and x is not an element of D. So in particular, the thing we care about is that x is not an element of D. And so that's what we wanted to deduce, right? So what we see here is, under the assumption x is an element of B, we have logically deduced x is not an element of D. So in other words, we have proven if x is an element of B, then x is not an element of D. But we know that this is the contrapositive of our goal. This statement is logically equivalent to saying if x is an element of D, then x is not an element of B. But that's exactly what we wanted to deduce, right? So putting this all together, we see under the assumption x is an element of A, we have logically deduced if x is an element of D, then x is not an element of B. So we've given a direct proof of this implication. And actually, just for emphasis, I'm going to say that we have shown if x is an element of A, then if x is an element of D, then x is not an element of B. And that's it. We have proven exactly what we wanted to prove, so this completes the proof. So now let's look at another example. This next example is going to involve numbers. Suppose x is non-zero. Prove if the cube root of x plus 5 over x squared plus 6 is equal to 1 over x, then x is not equal to 8. So, we're trying to prove a conditional statement. So one option we have available to us is we could try to prove it directly, right? Under the assumption that this equality is true, can we logically deduce that x is not equal to 8? Well, maybe, but let's try to prove the contrapositive, right? The contrapositive of this statement tells us if this is false, then this is false. Or in other words, if x is equal to 8, then cube root of x plus 5 over x squared plus 6 is not equal to 1 over x. It seems like the contrapositive might be easier to prove, because if we make the assumption x is equal to 8, we should be able to easily logically deduce that this is true, because all we'd have to do is substitute x in for 8 on the left-hand side, substitute x in for 8 on the right-hand side, show that both sides aren't equal. So let's prove the contrapositive. So for our scratch work, we're proving this statement. So let's make the assumption x is equal to 8. But then to logically deduce that these guys aren't equal, we're just going to plug x in for 8 on the left-hand side, plug x in for 8 on the right-hand side, show that they aren't equal. So starting with the left-hand side, this is what we have. In the numerator, that's just going to be 7. In the denominator, that's 64 plus 6, which is 70. And that's just 1/10. And as for the right-hand side, well, the right-hand side is just 1/8. So 1/10 is not equal to 1/8. So we're done. Now we're ready to get into our proof. Again, the first thing to note is that we're doing a proof by contrapositive. We're proving the contrapositive of this statement. So let's note that in our proof. So what that means is we're going to prove that this statement is true. So we'll make the assumption x is equal to 8. From here, we're going to logically deduce that this guy is not equal to this guy, right? But that just comes from plugging in x equals 8 on the left-hand side. If we do that, here's what I'm going to do. I'm actually going to write out explicitly what the left-hand side says, keeping the x's there. And now we're going to take everywhere we see an x and substitute x for 8. Right, and then we know that this just becomes 7 over 70, and I'll write that as 1/10. So this is equal to 1/10. We also know 1 over x is equal to 1 over 8. So I'm going to say, and 1 over x is equal to 1 over 8. So then the thing to note is that 1/10 is not equal to 1/8. So since these guys aren't equal, these guys can't be equal. And that's it. We have logically deduced what we wanted to deduce. So we see, under the assumption x is equal to 8, we've deduced that this is true. So we've proven if x is equal to 8, then these guys aren't equal. But we know by the contrapositive, this statement is logically equivalent to the statement we were trying to prove. So we can conclude if these guys are equal, then x is not equal to 8. So we've proven exactly what we wanted to prove. So this completes the proof. All right, so now let's look at another example problem. Suppose x and y are real numbers, and 3x plus 2y is less than or equal to 5. Prove if x is greater than 1, then y is less than 1. So we're trying to prove this conditional statement. So let's first try to prove it directly. So we'll make the assumption x is greater than 1. Right, so scratch work. Let's make the assumption x is greater than 1. Let's see if we can logically deduce that y is less than 1. We need this inequality, so how could we obtain it? We do have an inequality containing y. Let's write it down. Well, let's get y alone in this inequality. Right? If we algebraically solve for y, we will get y is less than or equal to 5 minus 3x over 2. Okay, so it's not saying y is less than 1, of course, but if we could show that this guy is less than 1, then that would imply y is less than 1. So let's see. Can we show that 5 minus 3x over 2 is less than 1? Well, in an attempt to show that, we could actually modify this inequality so that the left-hand side becomes 5 minus 3x over 2. Because notice, right, we have x greater than 1. We're pretty much going to take this inequality, multiply -3 on both sides, then we'll add 5 to both sides, then we'll divide 2 on both sides. That'll give us 5 minus 3x over 2 on the left-hand side. So, first, if we multiply -3 on both sides, that gives us -3x is less than -3. Adding 5 on both sides, that gives us 5 minus 3x is less than 2. Then we just divide 2 on both sides, we get 5 minus 3x over 2 is less than 1. So that's it. We see y is less than or equal to 5 minus 3x over 2, which is less than 1. Therefore, y is less than 1. Right? These two inequalities together imply y is less than 1. That's exactly what we wanted to deduce. So we could prove this statement directly. So let's do it. Let's write up the proof. So we're proving this implication directly. So we make the assumption x is greater than 1. From here, we are going to logically deduce y is less than 1, following what we did in our scratch work. What we did that was we observed, we took this inequality and algebraically solved for y. So basically we could just say, since 3x plus 2y is less than or equal to 5, solving for y, we obtain that y is less than or equal to 5 minus 3x over 2. But then, throughout the rest of our scratch work, we showed that 5 minus 3x over 2 must be less than 1. Right? We basically just converted our inequality x greater than 1 to 5 minus 3x over 2 is less than 1. So, basically we're just going to follow what we did in this chain right here. So, since x is greater than 1, multiplying negative 3 on both sides, we get negative 3x is less than negative 3. Then we add 5 on both sides of the inequality. We get 5 minus 3x is less than 2. Then dividing 2 on both sides of this inequality, we get 5 minus 3x over 2 is less than 1. So then, we observe, since y is less than or equal to 5 minus 3x over 2, and 5 minus 3x over 2 is less than 1, these two inequalities imply y is less than 1. And that's it. We logically deduced y is less than 1. So what we've proven here is, under the assumption x is greater than 1, we can logically deduce y is less than 1. So in other words, we have proven the conditional statement, if x is greater than 1, then y is less than 1. So this completes the proof. That is it for this example. We're going to look at one more example now. Let x and y be real numbers. Prove if x squared plus y is equal to negative 3 and 2x minus y is equal to 2, then x is equal to negative 1. So, again, we're trying to prove this conditional statement. So, let's try to prove it directly first, right? So, to prove it directly, let's make the assumption x squared plus y is equal to negative 3 and 2x minus y is equal to 2. From there, we'll try to logically deduce x is equal to negative 1. So, this looks like we have a system of equations if you've taken an algebra course. And yeah, that's essentially what's happening. So your gut instinct might be telling you, well, let's add these two equations together, right? Well, let's try to think about what that means, adding these two equations together. Well, basically, we're going to add x squared plus y and 2x minus y together, right? That's really what we're going to be doing, right? So, because if we add the two equations together, we're really taking x squared plus y and adding 2x minus y to it, right? And that should be equal to what we have on the right-hand side added together, negative 3 plus 2. Right, but why is this true? Why is this actually a true statement? Because observing what we have on the left-hand side, since x squared plus y is equal to negative 3, we can substitute this x squared plus y with negative 3. Since 2x minus y is equal to 2, we can substitute the 2x minus y for 2. That's why these guys are equal, right? That's what allows us to do this. But the observation is that the y and the minus y cancel out, so this is just x squared plus 2x. Negative 3 plus 2 is just negative 1. So this will give us x squared plus 2x equals negative 1. Adding 1 to the other side, well, that gives us x squared plus 2x plus 1 is equal to 0. Right? And you probably recognize this as a trinomial. And if you factor it, it's x plus 1 squared. So we have x plus 1 squared equal to 0. Right? So if you were to expand this out, that's equal to x squared plus 2x plus 1, as we know. So we have a real number squared equal to 0. What must x plus 1 be equal to? X plus 1 has to be equal to 0. Why? Why can't x plus 1 be something else? If x plus 1 was not equal to 0, that would imply x plus 1 squared is strictly greater than 0, right? Because any non-zero real number squared is greater than 0, right? So assuming x plus 1 is not equal to 0 will imply x plus 1 squared is greater than 0, contradicting that it's equal to 0. That's why we must have x plus 1 equal to 0, right? Or another way of looking at it is we could use the following result. I think this might actually be easier. Suppose we have two numbers, a and b. We multiply them together, it's equal to 0. That implies a is equal to 0 or b is equal to 0. Right? If a times b is equal to 0, then a is equal to 0 or b is equal to 0. Right? It's possible you can have both a and b equal to 0 as well. Right? It's just saying at least one of them is equal to 0. Right? So we can use that property here as well. Right? Since x plus 1 times x plus 1 is equal to 0, we're basically taking a and b to be x plus 1. So if x plus 1 times x plus 1 is equal to 0, therefore x plus 1 is equal to 0 or x plus 1 is equal to 0. Right? So one of these has to be true. Well, they're both saying x plus 1 equals 0, so we must have x plus 1 equal to 0. Right? So that's really what's happening here. So since x plus 1 is equal to 0, that implies x is equal to negative 1. So we're done. We could prove this conditional statement directly. So, to write out the proof, we first make the assumption x squared plus y equals negative 3 and 2x minus y is equal to 2. From here, we will logically deduce x is equal to negative 1. Now in our scratch work, we added these two guys together. But let's first note x squared plus 2x is equal to the sum of these two guys. So we're going to write this first, but then we know since this guy is equal to negative 3 and this guy is equal to 2, this is really just negative 3 plus 2, which is equal to negative 1. So you have x squared plus 2x is equal to negative 1. Then we add 1 to both sides. So we're going to have 0 equal to x squared plus 2x plus 1. And we notice that this is precisely x plus 1 squared. So I'm going to say that's equal to x plus 1 squared. So x plus 1 squared is equal to 0. We saw that that implies x plus 1 is equal to 0, just by this property. But since x plus 1 is equal to 0, we just subtract 1 to the other side, so we get x is equal to negative 1. So that's it. We've logically deduced x is equal to negative 1. So under the assumption x squared plus y equal to negative 3 and 2x minus y equal to 2, we logically deduce x is equal to negative 1. So we've proven this conditional statement. So this completes the proof. And so yeah, that's pretty much it for this video.